All right. Fantastic. Well, good morning or good afternoon or good evening, everyone. This is great to have everyone here. I see we have friends from Nepal and in the chat. Good evening to you. It is our really great pleasure to have this morning Dr. Stephanie Gora. Sorry, I'm mumbling here. She's an assistant professor in the Department of Civil Engineering at York University and is going to talk to us about some challenges and opportunities in small community and remote community water supply. So I will leave it at that and hand the mic to you, Steph. Thanks for coming.
Oh, thank you so much for having me. And thank you all for showing up. So today I like to take a bit of an interactive approach to my lecturing. So I want you to prepare to participate, and I really want to hear your opinion on a few different things and get your input. So I am an assistant professor of civil engineering at York University in Toronto. I've been working at this job since August 2020, so I am a nearly fully remote professor to date. We just started going back to campus. So this is a really cool thing. I think this is one of the cool things that has come to us through the pandemic is our ability to do these kinds of talks pretty easily, right? Like I'm in Toronto right now and you're all over the world, and how exciting that we can join one another to discuss this topic today. So the way I'm going to do it today, I'm going to give you a little bit of background on just water safety generally in Canada. I also want to give you some background as to my own experience working in small communities. And then finally, I want to talk about how some of this can be used in a really positive way. So I think that we talk a lot about challenges in small communities, as we should, because they're a huge source of drinking water risk in Canada and around the world. But one of the things I think gets overlooked frequently is the fact that there's also really interesting opportunities for innovation in this space. So in Canada, so my work has been until now pretty much restricted to Canada. I've looked around outside of Canada, but haven't done a whole lot of work there. I'm looking forward to doing a project outside of Canada this summer, fingers crossed, but to date it's all been in Canada, so that's where my expertise lies. Now, most drinking water advisories in Canada, when I'm saying drinking water advisory as opposed to boil water advisory, it says it on this graph here, because it's a little bit more, it's a bit of a wider term. And as time's been going on, it's not just boil water advisories that we're seeing in Canada. So nonetheless, for the most part, drinking water advisories in Canada are boil water advisories. And they almost all happen in small communities. This is a graph just from some data from Health Canada, looking at the size of population and the percentage of boil water advisories in Canada that are represented by communities of that size. So on the stacked bar graph here, we can see that there's the years across the bottom. The main things that stand out is these purple sections of the bar are the biggest sections almost all the time. And this is communities under 100 people. These are very, very small communities, and they're responsible for a disproportionate number of drinking water advisories. And most of the rest that happen are actually also happening in fairly small communities. The larger communities, which in this case are defined as over 5,000, which is actually still very, very small in Canada, are responsible for just a tiny fraction relative to the others. So now, a lot of the discussion around this comes from a lack of what we call capacity. Now, I've put it in a little quote, because I think that sometimes that's an overused term that maybe doesn't take into account that there are certain abilities and opportunities in small communities that don't exist in large communities. But nonetheless, there are issues related to just limited water treatment. Most of these systems are very minimal, oftentimes just chlorination. There's the small population means a small tax base and also a small number of people to draw, an operator from. So there can be a lot of issues on that end. One of the things that can also come into the conversation is that cultural norms and preferences can have a huge impact on how people feel about their water and how they interact with it. And this is true of all sorts of communities in Canada. So, we see that there are a lot of drinking water advisories in Canada. But what do you think the main reasons for that are? So this is where I want to get some ideas from you. Don't worry. I guess there are sort of some wrong answers, but not really. I just want to get your sense of what you think about when you think about a drinking water advisory in a country like Canada. So we're going to use a program called Mentimeter. The information has been added into the chat here. It's, has it been? Maybe we add it again. I don't see it there. So what you have to do is just go to menti.com. And don't worry about this link here right now. This is just so I can get there. So go to menti.com and I'm just going to show it. And once you get there, that's my work. That's my work. Okay. Here we go. You should have all the information you need right here. So go to menti.com and you just have to enter the code 47787605. And what I want to know is, what do you think the main causes of drinking water advisories in Canada are? I'll give it a couple of minutes. Thanks for sharing, Ketan. Bacteria. All right, great. I like that we're seeing some different ideas here. I'm gonna give it one more minute. I think we're getting a lot of great answers here, so lots of stuff to discuss. Okay, so I'm seeing a lot of mention about bacteria and water quality. That's cool and interesting. I'm seeing a lot of talk also about operator training, regulatory issues, and issues around kind of, again, that talk of capacity. So cool. I'm going to bring up my presentation again and go a bit forward. So now one of my students is working right now on a paper all about the different causes of boil water advisories in Canada. So we got some information from the Canadian Network for Public Health Intelligence, CINFI, and this was information from many, but not all, provinces and territories in Canada. The data we got was anonymized, which means we don't actually know exactly what community it came from or even what region. So I wanted to give those caveats because it may not cover every single drinking water advisory that's been that's in Canada. That said, we were able to find some really interesting trends. So this complicated graph shows a few things. So we've got a couple of different population ranges. So we've got under 500, so very small. We have 500 to 1,000, which is still pretty small, and then greater than 1,000. And the reason we did this kind of breakdown at the bottom end is because we already knew that most drinking water advisories happen in small communities. We also broke it down along the x-axis here. We're looking at the length of the boil water advisories, right? There's a lot of talk of long-term boil water advisories, and based on our looking at it, that's a good idea because some of them last a really long time. We had some that lasted, we had a 15-year data set. We had some communities that were on boil water, drinking water advisory the entire time. So 15 years, that's a very long time to not be able to drink your water without further treatment. Most of them, though, were often somewhere between a week and a month, which is still incredibly long, especially if this is something that if you've got children at home, if you're running a business, this is hugely disruptive. So another thing that really stands out is that if you look at this purple section here on this on these stacked bar graphs, this means line break or pressure loss. There are a couple of different reasons that can underlie that, but what the main takeaway is that this is actually a distribution system issue. So it's not that there aren't boil water advisories related to bacteria being detected in the water. It's not that it's not because of operator training, because there certainly are a lot that are related to that. But a lot of what we're seeing is related to the distribution system infrastructure. And a lot of times what happens is that if something goes wrong, like if there's a pipe leak or there's a broken pipe, they'll put on a precautionary boil water advisory. So people are told to boil the water because the operators are not confident that there's not an opportunity for there to be contamination. This is useful information because if we really want to deal with what's happening here, if we really want to minimize the number of drinking water advisories, we need to know what is causing them. So similarly, oh, no, I didn't put it up, sorry. Forgive me, I had another slide, but I didn't want to get too long. We also looked at repeat boil water advisories and we had a very similar pattern. So again, issues in the distribution system were the main cause of drinking water advisories being called. And in most cases, those were precautionary, which means that it's not that something had been detected in the water, but that there was a risk of there being something detected in the water. Okay, so with that in mind, I want to tell you about two projects that I've worked on in the past and kind of how, I guess, where I went from somebody who didn't know a lot about drinking water in small communities. I'm from Hamilton, Ontario, which is about 500,000 people. So this is not something that was in my own personal background, but I've done a lot of work since I started as an engineer in these kinds of communities. And I think when I first started, all I saw were the challenges, but as time went on, I started to see the opportunities for innovation. So the first one, when I worked in industry for 3 years a while ago, and a lot of my work was related to small communities in Newfoundland and Labrador. So if you're not from Canada or you're not super familiar with Canada, Newfoundland and Labrador is our easternmost province. It has one of the smallest populations in Canada. So it's one of our, and it's very rural. Or even, I think the name rural, the word rural sometimes implies like farming, but it's almost like more remote. There's a lot of small fishing villages that dot the coast. The main industry there historically has been fishing. So this is a picture of one of these communities, and this is pretty representative. Here we've got, this might be Port Basque, so don't quote me on that. My colleague took this picture. But you can see that there are numerous buildings. It's a very small community. It's right on the ocean. And again, most of these communities grew up as fishing villages. That was the purpose, is that the main industry here was people fished. Now, there are a couple issues with drinking water here. I mean, I think you can probably already imagine the capacity related issues that we've talked about, right? It's small population, it's hard to get tax dollars, it's hard to get, just because of the size of the population, the chance that you're gonna have someone who's really interested in operating the plant and has the educational background is less than if you were in a community of five 1 million or 500,000 people. But there are also other issues that really complicate the situation in Newfoundland and Labrador. So it's called the Rock, and it really is very rocky. It's difficult to get deep. And a lot of the lakes and rivers that do exist, it influences their, I guess, chemistry in such a way that they have very high levels of organics, natural organic matter. So that's the stuff that kind of makes the water like brownish. They have pretty high levels of metals, and they have low pH and low alkalinity. And then in most cases, there's just chlorination as treatment, and it's a very limited amount of chlorination as well. So the water that people get into their homes is generally pretty unappetizing. It has a strong chlorine odor, it has a color to it, and a lot of people don't use it as a result. Like they'll use it for their bath or for their laundry, but they won't use it to drink. So this is obviously a problem. People are unhappy with it. And those aesthetic considerations are also kind of masking, or at least they're the main indicators of other kind of bigger problems that underlie the water. When you have a lot of natural organic matter and you add a lot of chlorine to the water, you're going to end up with disinfection byproducts. And the levels in many small communities in Newfoundland and Labrador are through the roof. Like levels like 3,000 3 milligrams per liter, which is way, way beyond the recommended level or the regulated level in, say, Ontario. Because the chlorination system is the only thing there, the opportunity, the ability to remove bacteria and other pathogens can be less, right? So there is a perceived risk that people perceive because it doesn't smell good and doesn't look good. But what they're right. their perception is correct, that there are some issues underlying it. But again, we've got these capacity issues. And how do we solve this kind of problem? Can we really be putting in a multi-million-dollar water treatment plant for every single community in Newfoundland and Labrador? Well, the answer is no. But there are other things that are possibilities. So for a fraction of this cost of putting in this full-scale treatment system, Some small and remote communities can install what we call a potable water dispensing unit. The idea here is that, in a big city, what we usually see is water comes in, goes to a centralized water treatment plant, and then goes directly to the house or building. Now, with a potable water dispensing unit, we have some water leaving the centralized treatment system, and that's going to go for non-potable uses in the home. So things like toilet flushing, laundry, whatever. But there's also a potable water treatment system, and it's usually located somewhere in a central location in the community. And people can go and fill up their, like a jug with this water. And it's very high quality water. So I was lucky enough to work on this project throughout my time in industry. So it's one of the first things I did, and it was also some of the following up projects were some of the last things I did while I was there. So what was neat about this is that it wasn't an idea that was imposed from above. This is something that came from the communities themselves, or at least a subset of them. So 7 communities built their own potable water dispensing units, usually at things like the town hall or whatever. 3 of them had ozonation for their treatment, and 4 of them used reverse osmosis membranes. The aesthetic water quality, so that there was no more taste or smell of chlorine. The types of treatments used meant that there was much less color in the water. So the aesthetic quality was much higher. We did a study looking at all 7 of these. We went to sample the water and to talk to people and figure out how people were using it. And we found that the aesthetic water quality was a huge predictor of whether or not people would actually use this thing, which is, again, not too surprising. Aesthetic water quality is what gives all of us as users an indication as to whether or not the water is safe, right? We also found that we called it the quality of the dispensing experience was a huge predictor of whether or not people would use it. So they had different ones. These are a couple of different dispensing experiences that people could have in these communities. So you can see that, some of them just look like a tap. Some were indoors, some were outdoors. This last one here is pretty fancy looking. And we found that people were much more likely to use the potable water dispensing unit if they had this nicer dispensing situation. So when I talk about innovation, we saw these things. It came from the ground up. And we were tasked as an engineering firm with designing something that would take into account kind of what's already been done there, like before in these 7 communities, and how could we improve it, standardize it so that it could be scaled up to many more communities in the province. So I won't go through this in too much detail, but it does show you the main components of this process. We have ozone, we have activated carbon, we have nanofiltration, we have UV. First thing that probably stands out here is that, wow, there's a lot going on here, right? We had multiple advanced processes. They were very small, which kind of helped on the energy and chemical side, but still we had a lot going on. The goal here was that if one of these things broke down, it would still be possible. There was kind of a natural redundancy built in so that the other stuff would keep working and still provide safe water. 2 other things was that we had this storage. We sized the storage so there would be at least 5 liters per person per day for the community. And the UV disinfection, when the water came in, it would have had chlorine in it, but through all these different stages, it would have been removed, especially through the GAC. But we did provide UV disinfection right at the outlet. So after it came out of storage, right when someone's dispensing the water, it would go through a UV unit. So again, this is kind of my first experience of, wow, we have this kind of terrible situation. But the solution is kind of outside the box, right? Or I guess we're making a new box, but it's not what you'd expect, right? And that's kind of cool. It means that there's not just, I don't want to say there's freedom, because that implies that maybe we're going to play fast and loose with water safety, and that's not really what it is. It's just that you might need to look outside the usual solutions, and there's maybe a certain kind of openness to trying new things that will work at the small scale. So I was lucky, even when I started my PhD, I left the company and I moved to Toronto to do my PhD. And but I did get to go back after a few of them were built. And so here's a picture of me standing in front of one of them, one of the standardized ones. And so they're just this is literally what it looks like. There's a parking lot. People drive up with their car and their jugs and they fill them up. Yeah, so that was a really neat project. And I kept an eye on this because I still think it's so cool. I constantly talk to the guys I used to work with and I'm like, how's it going? So this is a paper that I found for another reason. A group that had done some work up in Rigolet, which is in northern Labrador. And so this community had a potable water dispensing unit. And I won't go into the details too much, but the main takeaway here is, well, two. So one is that here's our nice standardized system. Actually, I've got three. Next one is that these 3 glasses of water, this last one is the water that comes out of the potable water dispensing unit. And you can see it's much more appetizing than the raw water that comes in from the lake and the water that comes out of the main treatment system. And a big one here is that when people had access to the potable water dispensing unit, it really replaced certain other types of water they've been using. So people were already using some tap water, and a lot of people were relying on bottled water, and some people also like to get water from the land. When the potable water dispensing unit became available with its much higher quality water, you saw that all these other sources decreased. And the one that really gives me heart is the bottled water, because bottled water is expensive and obviously causes a lot of plastic pollution. So this was a major positive in terms of people being able to turn from a very expensive source of water to something that was less expensive for them. Okay, so the other case study or experience I'd like to relate for you is my work that I did during my postdoc. I was really lucky to be assigned this project. I was working in Halifax at Dalhousie University with Professor Graham Gagnon. And this was the project I was brought on to manage. So Pond Inlet, or Midi Metallic, is a community on the northern tip, basically, of Baffin Island. I think that might be slightly, my arrow might have moved slightly when I changed the formatting, but anyway, it's up there. And it's a beautiful, beautiful place. Community is, I think, about 1,500 people. I think 90% Inuit, and the mountains here are Bylot Island, which is why I'm thinking my arrow might be a bit wrong, because it's this island right here, and it's just across the bay. It's spectacular, spectacularly beautiful place. So like many places in the north, Pond Inlet has a trucked water system. So what this means is that instead of having pipes in the ground, they rely on a truck to deliver the water. Water comes in from the lake. It gets pumped and then as it's going through, there's some chlorine added and it goes into the truck. The truck drives around for 20 minutes for chlorine contact time. And then it delivers the water to tanks in people's homes and in other buildings. And then once it's there, your dispensing experience is very similar to what you would have in the south in a larger city. You turn on your tap, the water comes. The difference is that you have to be very careful with how much you're using, because if you let your tank get too low, you're not gonna have enough water. Thankfully, in Pond, as well as many other communities, it's not the end of the world. There is like a schedule for getting water to people. You can also call a number and they'll come and give you water basically right away. So our project was to identify kind of main areas of risk as well as the hazards that existed in those areas. So one of the first things we did was look at biological activity. In this case, we used something called cellular ATP, which is an indicator basically of that biological activity. It doesn't tell you who's in the water, but it tells you how active everyone is in the water. So this means that there could be some dangerous, like pathogenic organisms, but there can also be, and usually are, mostly non-pathogenic organisms. So this figure here shows the results we got from the pump house. So the first place here, the truck, the tank, and the tap. And then we also had 5 sampling events. And you can see that the results we got were a bit different depending on where we were taking the samples. So in the pump house, which is untreated water, it's just coming out of the lake or reservoir, you see that there's a pretty much the expected seasonal behavior. So we're at February, everything's frozen over. You get to May and July, and there's higher biological activity. Again, not surprising. This is when the ice is broken up. As you get into the fall, it goes lower. We had very low biological activity in the truck, fairly low in the tank. We did have something going on in a little bit in the spring, but especially in the summer. We did a little bit of other analysis that I'm not going to go into in too much detail. One of the things we found was we did a bit of DNA analysis. And what we found is in some of the tanks, there was some evidence there might be some microorganisms living at the top. They were not pathogenic. They were just the kinds that would unfortunately lend a really bad smell to the water. And we think, although we have not followed up on this or proven it, so we think, but we do not know. It is a hypothesis that those might be the bacteria that were causing this biological activity. And this is supported by the fact that we had very low biological activity at the tap. So the tap water comes from the bottom of the tank, and the samples we took from the tank were from the top of the tank. So we think there might have been something going on there. Pardon me. We also looked at metals in drinking water, and this is where I personally had the greatest concern. Was these are our lead results. Once again, we've got a couple of different sampling periods that we had, and I've got this I guess pinkish orangish line here is showing 5 micrograms per liter, which is Health Canada's recommended lead level right now. And you know, many of the samples were below, which is great. And also note that this, though, is a log graph. So the ones that were above were quite a bit above. And this is a little bit scary, right? We have some places in the community where if someone turns on their tap, they're likely being exposed to quite a bit of lead. Now, this is maybe a bit surprising. There is a truck that delivers the water, not pipes, right? Usually we think of lead as coming from the distribution system. But in this case, it was from the premises plumbing. So things like solder that have been used to fix the pipes, and maybe some of the fittings or other elements of the domestic piping, plumbing system. So we reported the elevated levels to the territorial government, and they did come in with some point of use filters for these communities, which was a huge relief. But it was still just interesting to see it. And I'm just glad that we were able to catch it and they were able to do something about it. Not going to get into these. Oh yeah, sorry. This is interesting though. So we did a bit more exploration with the lead. And in this case, we were doing what we call sequential sampling, and which means that we would go through and we would take a sampling. We turn on the tap after it had been sitting in the domestic piping system for a bit. And then we would like take 500 mils, 500 mils, 500 mils, 500 mils. I think it was that much. Yeah. For each point. And it kind of gave us like a map of the piping system and could show us more or less where maybe that lead was coming from. So you can see here that this is 2 different buildings. I'm looking at the purple here. And one of these buildings is one that had quite a bit of lead. And you can see that there was, you know, as we turned on the tap, it was almost immediately, there was a big plug of lead containing water. And then as the tap was flushed, that decreased because the water was now coming directly from the tank. And that line, the dotted line there, represents the lead level in the tank at the same time. And then this other building, which was a much newer building, had very, very little lead in the water. So one of the other things, what did I want to say about this one? Sorry, I'm just going to move on. Oh yeah. Okay, so 2 other things I want to outline about this in terms of like vulnerabilities in Pond Inlet specifically, is that there are a lot of people involved. So we've got these challenges, and then we're like, okay, how are we going to solve it? You know, best practices is to like, who's involved here and who's responsible for what? In this case, as in many, many places, not just small places, it's actually a huge number of people are stakeholders, and the governance structure is very complex. So what this means is that if we're going to come up with a solution, oftentimes you have to go through a lot of different people, and there are a lot of different people to take into account and consult with. Oh, that's what I wanted to say. Sorry about that. No, we'll just leave it. I'm sorry. I'm trying to go faster than I intended, getting myself a little turned around. Okay, so summary of challenges that we found in Pond Inlet. The system design made it vulnerable to microbial contamination. There were metals in the drinking water that we linked to the premises plumbing. Lead was our major concern. Oh, that's what I want to mention. This is a community that experiences frequent boil water advisories. There is a perception that there's very low capacity for drinking water management in the community, and that is evidenced by repeated boil water advisories and other water quality emergencies. And finally, there's a very complex governance structure. So in the next few sections, I want to talk about these first 3. I'm not going to bother with, no. Governance is hugely, hugely important, but it's something that as an engineer, we are usually not able to take the lead on. So I want to focus on these other 3. Okay, so innovation. So, you know, going to this Pond Inlet problems, because I'm going to stick with Pond Inlet for now. You know, we found this vulnerability to microbial contamination what can we do? What can we do in this situation? So that's what my research group is basically focused on, is trying to say, okay, let's understand the problems. And then what kind of technological solutions can we come up with that might address these challenges? So one of the ones that we're looking at is UV LEDs for point of use and point of entry treatment. The idea being that we could have it, it's not almost like, it is exactly distributed treatment, which would mean that it's not at a centralized plant, it's at different locations within the system. So this is something that my student David Kim worked on as his summer project last year. So if you haven't heard much about UV LEDs, I just saw Nathan Moore signing on, so there's at least one expert here. They're basically very, very small UV light sources. And the cool thing about them is basically that they're small. Also that you can choose the wavelength, and also they turn on and off really quickly. And this is hugely promising because it can change the way that we design reactors. So David's work, he reviewed a big pile of studies about what was going on with UV LEDs right now. He identified different vendors, reputable vendors, and there are quite a number of them. I have Aquasense's thing here, but only because I've worked with them, and so I was able to take a picture of their unit, but there are lots of different vendors who are working in this space. So one of the coolest things that David did was he talked to a bunch of different industry, experts. And so he talked to consulting engineers, he talked to regulators, he talked to people at the Washington Clean Water Center, and he talked to manufacturers of UV LED reactors. And what he found was that there's a bit of a reluctance to adopt this kind of technology among people who are not right in the UV LED industry. And a lot of this is because there's not a lot of pilot data or real world installations, and people want to see that before they will basically sign on to this technology. So another thing that we've been looking at is, it's one thing to have a treatment, but how do we make sure that the water is always safe at the tap? So another thing that we're working on, this is my student Sarah's project, is a microfluidic sensor. In this case, she's looking at something that would be used in concert with a UV LED reactor in order to better understand or be able to calculate how much in an activation we'd be achieving, or how well the thing would be working. So this is another really cool high-tech potential solution to a problem that exists in many small communities, which is this vulnerability to microbial contamination. And this is our plan. So I just put in an application with a student who will hopefully be doing this work, designing a pilot system that we can use to basically test these technologies. So I think of UV LEDs as kind of emerging technology, and the microfluidic sensors as like something that's really novel. So the nice thing here is that we could test both of them on a skid, and the idea would be to have it so we could move it around and test it in different locations. So fingers crossed that student gets his scholarship and can come help with this. All right, now how about the metals in drinking water, right? This was a major problem, and in my opinion, a bit of a scarier problem that we uncovered. So right now, what we found, I showed you a couple different things, right? I showed you a longer graph that had some really high lead levels, and I also showed you those smaller graphs that were the sequential sampling. One of the things we found when we were up in Pond Inlet was that it was very difficult to get samples that were really representative of the problem we were trying to understand. A lot of the sampling procedures that already exist are designed for cities, and designed not only for cities, but for systems that have a pipe distribution system. So one of the things that we want to look at as a team is, can we develop better sampling methods that give us better information that we can use to understand these problems, so that we can then come up with interventions that would be more effective? So this summer, Kyle Baird, who's a undergraduate student, and Caroline Duncan will be helping him out as part of her project. She's a PhD student. They're going to be looking at 3D printing a proportional sampling apparatus. And the idea here is that we could attach this to a tap, and it could take constant samples, which would really give us a lot of information about how much lead is coming out of taps, right? We're not relying necessarily on, I don't want to say, it is carefully thought out, but it's not like a set method. This is trying to get just a better sense of overall what's going on. And then we're going to try to match it up with different existing sampling methods and see kind of which one might be best for these kinds of systems. Also, I just started working with a new student, Shapur, as well as a professor in mechanical engineering, Puya Rezai, and we will once again be looking at a microfluidic sensor, in this case for lead detection. Okay, how do we solve this lack of capacity issue? So something that's been proposed and implemented by various countries. It was originally proposed by the WHO, the World Health Organization, is water safety planning. This approach guided some of our work in Pond Inlet. The idea here is that we get a better understanding of the system. We also talk to people. A lot of it is about talking to people and understanding where the different hazards exist. So we talked to people, and this is just an example of one of the exercises we did where we talked about all the potential hazards surrounding this one area of risk, which was the truck, the delivery truck in Pond Inlet. And we went through, it was the research team at Dalhousie as well as the research team in Pond Inlet, and we identified all these different things and sort of talked about them in detail. Later in the project, we actually didn't just limit it to our research team. We talked to people in the community as well as other stakeholders. So engineers who were working for the government, people working in things like public housing, who had a lot of influence on the water quality in different buildings. So we actually talked to them, and we talked to them in their own language. They had the option to be interviewed in English or Inuktitut. And we got a lot of information about what they perceived as hazards in their water system, as well as ideas they had for addressing it. So I think that water safety planning, or maybe something similar to it that's a bit less onerous, is a really, it's not that new, but it's something that holds a lot of promise. And it's kind of an innovative-ish approach to water management. I think in our space that a lot of us work in with this WASH type stuff, we've thought about water safety planning for a long time, but if you're working in industry, it's not really something that comes up too much. It has been adopted to some degree in Alberta, but it's been converted into a very numerical type thing, so it doesn't really match the original intent of the WHO document. So another thing, kind of going down this road too, it was great that we were able to, as a research group, and again, we were split between, we had a community representative who was the local research manager, and we had the research group at Dalhousie. But it wasn't like, we did some research that I would say is fairly inclusive, but the research team up north had already done some of their own research. And so it's not just about listening to people in a short conversation. There's also a lot of knowledge that exists and has been documented in different ways that's there, so it's again, kind of this matter of listening to people. And that's why I say it's like water safety planning, but maybe there's something else that's additional to water safety planning. But I think that's probably where we're going to find solutions to this lack of capacity. And maybe we're going to find more capacity in communities than we originally thought was there. Okay, so we have 20 minutes left. I'm going to check the chat. So I'm going to answer the one question in the chat, and then I have an activity for us to do. So the question I have from Anne is, did we get a chance? Okay, I'll answer a few questions, and then, is that okay, Katana? Can I do a few questions and then an activity? Or do you want me to just do questions?
No, go for it. They're flooding in, so.
Okay, so let me do let's do 10 minutes of questions, and then we can, if we're feeling it, we can do a fun activity. Okay, so first question, did you get a chance to check manganese concentrations as well? We did. And there seemed to be something of a seasonal impact